Okay, here is the answer to the trick to know when you're doing the Sieve of Eratosthenes, how you can know when you're done and all the numbers remaining on your chart are prime numbers, without having to actually go through and test them all. To see where this idea comes from, we're going to kind of explore some other things with some different numbers, and hopefully it'll kind of become clear. I'm going to return to the number 24 that I did earlier. And what we were doing was we were looking for ways to multiply to equal 24. In addition to that, though, I could have said it a different way. I could have said, what are the factors of 24? What are the actual numbers I can use just as a list that will give me 24? So instead of writing equals here, I'm going to think of this as a set, a collection of numbers. And again, we started with 1, and we said 1 has to be one of those numbers because 1 times 24, which means 24 is also a number. But I'm going to want my list to be consecutive, so I'm going to go ahead and write 24 out here. Okay? And I know it can't be any numbers bigger than 24, because if you're a factor of a number, you've got to be at least that number. You've got to be at most that number. Mostly you're smaller. Okay? Then I just go in order. Check 2. Does 2 go into 24? It does, because 2 times 12 is 24. So I can write 2 as a factor, and I can also say 12 as a factor. All right, check the next number. 3. 3 goes into 24, so 3 is a factor, and because it's 3 times 8, 8 is a factor. Okay, check the next number. 4. 4 goes into 24, because 4 times 6 is 24, 4 is a factor, and 6 is a factor. Now check the next number, 5. Does 5 go into 24? No, it does not. Not nicely. So we don't count 5 as a factor. What's the next number? 6. Does 6 go into 24? Well, obviously, we've got it right here. So we know 6 times 4 is 24. Do I need to keep going through the rest of 24? Hopefully you can see the answer is no. Because if 7 were a factor, well then it would have to be 7 times some number smaller here. But we've already found all the numbers in this range that are factors of 24. Same with anything 9 through 11 or 13 through 23. They would have to multiply by some number over here, but we've already found all those numbers. And so as soon as I hit a number that repeats, I'm done. So I only needed to test, really, these first, you could say, 5 numbers, because we tested 5 to see. And then I'm saying, oh, okay, well, I'm good with that then. All right? So my key number was kind of 5. All right? So I'm thinking with 24, my key number was 5. Let's look at another number then. All right? Let's look at a big number, like 100. What are my factors of 100? Well, again, I know 1 is, and I know 100 is. Okay. Is 2 a factor? Sure, 2 times 50, okay? 2, 50. Is 3 a factor? No, 3 goes into 99 and into 102, so not 100. How about 4? Yes, 4 is, because it's 4 and 25. Okay? How about 5? Sure is. 5 and 20. I did not leave myself enough room. But we're going to be okay. All right, is 6? Nope. 7? Nope. 8? Nope. 9? No. 10? Aha, 10 is. 10 goes right here, so this is my bad. I didn't do this right. But it's 10 times what? Well, it's 10 times itself. 10 times 10 is 100. Okay. Do I write it twice? No, it's just a list of what are the factors, so I only want it in there once. So do I have to keep going at this point? Well, think about it. These are pairs of numbers, just as these were, and when I got to 4 and 6, as soon as I would check 5 and then 6, I realized 6 is already there, so I was done. Well, 10 and 10 are the pair. So if I go beyond 10, I'm going to start checking 11, but that means it'd have to be 11 times something smaller than 10. And 12 times something smaller than that, and 13 times something smaller than that, which means I'm checking with something backwards, and I've already found everything down here. So here, 10 is my magic number. I stop at 10. I don't need to look for any more factors after that, because I've repeated myself. Okay, should we do this one more time? Or do we see what's going on here? The trick is we're thinking about when do those repetitions start. Well, in mathematics, we say when you take a number and multiply it by itself, you're squaring it. Okay? So if I take some number x and I square it, and then I get some value y. Okay? But I might say, what if I know y, but I want to know x? So what if I know y is 100? How do I find x? Well, that's where we do what's called the square root. You undo the square. And you're probably used to that symbol. We say it's like that. And we square root that. Now here I'm focusing on natural numbers, so I don't care about negatives, so please don't yell at me in the comments. So I'm going to say that the square root of x squared, which is x, equals 10. I know that 10 times 10 equals 100. Notice how 100, 10, 100, 10. 24. 24 is not a perfect square, but we know something about it. Okay, I can write this inequality here. 16 is less than 24 is less than 25. Okay, that's obvious. And I can find the square root of all three of those. Okay, that keeps the inequality valid. So I can say let's square root all three of these. And I know the square root of 16. Because what times itself equals 16? Well, that's 4. 4 times 4 is 16. And I know the square root of 25. Because what times itself is 25? Well, that's 5. 5 times 5 is 25. In other words, I can say that the square root of 24 is between 4 and 5. But because it's bigger than 4, I have to check 4. Okay? And actually, I know that it's less than 5. So here's what's really crazy. When I came to this point, I said 5 was the magic number. I was actually being too liberal. 5 is not the magic number. 4 is. Because I know that the square root of 24 is less than 5. So the largest number that could be multiplied by itself to equal 24 is somewhere between 4 and 5. 5 is too big. It's 5 times something smaller than 5 would equal 24 if we're counting all possible numbers, not just natural numbers. So therefore, I could stop at 4. 1, 2, 3, 4. There's my list. I know I'm done. Oh, interesting. Okay. Here I did have to go up to 10 because I had to include 10 because I knew the square root of 100 was 10. But then it gets even better. If I want to drill down and find all of the possible prime numbers that could go into another number, I don't need to check for composite factors. I don't care about composite factors. Those mean nothing to me. So I don't care about the number 1. It's not composite, but it's also not prime. Okay? But I also don't care about the number 4. Because 4 is a composite number. 4 is just 2 times 2. And so really, I just needed to check up to the largest prime number that was less than or equal to the square root of my initial number, 24. Well, my square root of 24 is somewhere between 4 and 5, but 5 is too big. So what's the largest prime less than 5? Well, that's 3. So I only really need to check on prime factors up to 3. So my magic number gets even smaller, less things to check. And again, still the same thing here. I said 10 is a square root, but 10 is composite. What's the largest prime less than 10? Well, that's 7. And so my magic number for 100 is actually 7. So what this is saying is that it's not possible that there are any prime number factors greater than 7 that go into 100. Which means that all of the numbers less than 100 that are not multiples of the prime numbers less than or equal to my magic number are prime. And so when I was doing the Sieve of Eratosthenes before, and we did all the multiples of 2, all the multiples of 3, all the multiples of 5, and then all the multiples of 7, and I said we're done. I said everything else left here is prime. That's because I knew the square root of 100 is 10, and the largest prime less than 10 was 7, because the next one that wasn't circled was 11, so I knew the rest of them had to be. So if my chart were of size 24, if I only had a grid of 24 numbers, then I would cross off the multiples of 2 and the multiples of 3, and all the numbers remaining on that chart would be prime, guaranteed. So the same basic idea. If I were to have a chart of size, let's say 10,000, okay, so I want to find all the prime numbers less than 10,000. I can use the Sieve of Eratosthenes, and although that might seem cumbersome, and it is a little bit unless you're really bored, it's not going to be as bad as you think. First, find the magic number. So the first thing we do is we have to square root it. So again, I say, what number, when squared, will give me 10,000? Take the square root of both sides, and again, I only care about positive numbers because I'm only focusing on natural numbers. And I get x equals, and if you don't know this already, it is 100. 100 times itself is 10,000. And then I say, what's the smallest prime number less than 100? And if you remember the chart we did, we showed that it was 93. So my magic number for 10,000 is 93. And so all I have to do is on my chart of 10,000 numbers, 10,000 natural numbers, is I cross off all of the multiples of the prime numbers less than or equal to 93. And everything else that's left is a prime number, guaranteed. And that's how you can use the Sieve of Eratosthenes in a faster way.